All right, let's carry on with this shear and bending stress example. So what we'd like to do next here would be to find the centroid of the beam cross-section. So why don't you go ahead and do that, and then we'll have a look. All right, so let's look at how we could find the centroid. Now what you would do there is break the beam cross-section into two pieces, the lower rectangle and the upper, and then you'd want to find the area of each piece. So the lower there is 9 centimeters by 4 centimeters. So that would be 0.0036 meters squared for the area. The upper area would be 8 centimeters by 18. So that would be 0.0144 meters squared for the area. And then you want to find the distances from the base of the rectangle, or of the beam, to the centroids of each. So this lower rectangle has a height of 4, so the centroidal distance would be half of that. It'd be 2, so that'd be 0.02 right there. And now the upper one, you're going to take half of 18 and get 9 centimeters, but you have to add the 4 to it because you're coming from the base up. Okay, so that's 0.13. That's half of 18, which is 0.09 centimeters, plus the 0.04 that gets you to the base of the upper rectangle. All right, now once you've got that, you've got the numbers. Now you can put that into a little table. We've got the top rectangle number 1, the bottom one number 2. We got the areas that we calculated. We got the y-bar distances from the base of the beam to the centroids, and then we multiply those together and get y-bar A. Add those up and you get the total. Divide by the total area here, which is the sum of these two, and you get the centroid, 0.108 meters. Okay. All right, now the next thing to do is to find the moment of inertia of the cross-section about the neutral axis. The neutral axis is the centroid for the beam. It's the line at this height above the base of the beam right there, the 0.108. So once you go ahead and find the moment of inertia of the beam next about that neutral axis. All right, so you could pause and do that. So let's have a look at how to get the moment of inertia. So here's the calculation here. So what you do is you find bh cubed over 12 for each rectangle. So for the upper one, it's 0.08 times 0.18 cubed over 12, 38.88 times 10 to the minus 6. For the lower one, it's 0.09 for the base times 0.04 cubed that's the height cubed, divided by 12. It's 0.48 times 10 to the minus 6. Then you want the area times the offset distance between the neutral axis, which is right about here at 0.108, to the centroids of each of the shapes. Okay, so the top rectangle centroid is at 0.13. The neutral axis is at 0.108, so the difference is 0.022. That's the distance, the offset from the neutral axis to the centroid of the upper rectangle. The lower one, what you would do is you would take the 0.02 minus the 0.108. So what you're doing there is you're taking the 0.02, that's the height to the centroid of the lower rectangle, and looking at the difference between that and the centroid. So that's a negative 0.088. The negative really doesn't matter that much because you're going to square d anyway. It'll just go away. But that would actually be a negative 0.088. So that's that distance I'm showing right here. So now you got d and you got a. So you take a times the square of d. Got those numbers there. Add them to your original bh cubed over 12. And you'll get the total moment of inertia for each shape. So you're just adding these numbers together to get these. And then you just add this column up to get the total moment of inertia of the entire beam. Okay, so that's 74.2 times 10 to the minus 6. All right, now let's find Q. That's the first moment of area, it's called. That's what's used for when you do the shear calculation. So what you want to look at for Q is the area that would shear off times the distance from the neutral axis to the centroid of that area. So you just multiply two things together, you'll get a unit of meters cubed on that, and that's Q. It's used in the shear formula. So why don't you pause and give that a run, and then once you've got it, start the recording up and we'll go through it. All right, let's have a look at Q. All right, so we're going to look at the area that would shear off, and that's this area. If the beam were to fail at point 1 and we're finding the shear at B1, that's the area that would shear off. Okay, so that has an area of the base of 0.09, the height of 0.04, so that's 0.0036 square meters. Then what you want to do is find that distance you found earlier. What we're doing here, we're coming from the neutral axis, measuring down to the centroid of that area. Okay, so you're at 0.108, that's where the neutral axis is that I'm drawing right here. And you're coming down to the centroid of the area that would shear off. Now the height of that area is 0.4 centimeters, so the centroid's 2 centimeters up from the base. So that's 0.02 minus the 0.108. That's actually a negative 0.088, although we don't really worry about the sign too much on that. So to get Q, you take the area that would shear off, multiply it by that distance, and you get 0.0003168 cubic meters. Okay. So that should get you all the information that you need essentially to find the shear at point B1. So once you find the shear stress at B1 next here. Okay, so you can pause and give that a run, then we'll go through it. All right, let's have a look here at the shear stress. What we've got here, we've got a few things to plug in. Here's the formula, VQ over IT. So you want the shear at B, that's 24,000. You want the Q that we found earlier, and you want to divide by I, and then the thickness of the beam at that location, 0.1, that's just that distance across the beam, that's 0.08 meters. Multiply that through, and you get a shear stress of 1.28 megapascals. So that's the shear stress at point B1. Okay. Now let's find the bending stress at the maximum bending stress for the beam. Okay, so that sigma is MC over I, so you need M, you need C, and you need I. So you're going to need C to the top of the beam and C to the bottom of the beam measured from the neutral axis. All right, so you can go ahead and work through that and pause while you do it, and then start the recording up and we'll go through it. All right, here's the let's go through the bending stress now. Now here's the moment diagram. You'll notice that's positive moment throughout this entire span of the beam. What that means is the beam bends down like this. Okay, when a beam bends down like that, you've got compression on the top and tension on the bottom. It stretches on the bottom as it bends, that lengthens out a bit and stretches. It pushes it on the top, and that's compression. So when we calculate this, the compression's on the top and the tension's on the bottom. Now again, we've got our neutral axis here. We're going to want to find our C values, which are the distances from the neutral axis to the edge of the beam. To go to the top there, let's see. So what we've got here, we've got 0.108 for our height of our centroid of the entire beam, and that's where the neutral axis is. But what that means is C going down to the bottom will just be 0.108. Okay, that's how far it is from the neutral axis to the bottom of the beam. The further you are from the neutral axis, the greater the stress. So we want to find the maximum stress, and this will be the tensile stress on the bottom. Okay, what we would do, we would go and use this 0.108 distance to the bottom of the beam. Now, to go up to the top, we want to take the entire height of the beam, which is 0.22, and subtract off the 0.108, and we'll get 0.112 to the top. And that's the C you would use to find the tension, which is at the top of the beam. So we've got tension up there, compression there. So there's our C for compression from the neutral axis. There's our C to the top for tension for our neutral axis, from our neutral axis. Okay, and then you just plug everything in. Okay, so the formula is MC over I. You take M max, multiply by your appropriate C, C top for compression, C bottom for tension, divide by I for the beam, and you'll get the stresses at the top and bottom of the beam. Okay, so there's a run through shear and bending stresses for a beam.